Hello. Hello. Happy New Year, everyone. Good to see you all. Okay. We're about to start. And okay. Let me start. Let me start and share my screen. Okay. Perfect. You should be able to see my screen. You should be able to hear me and see me. I'll switch on the chat. And I'll switch on okay. Excellent. Okay, so today we are going to talk about elastic potential energy and oscillations. Okay. Oh. What happened? What happened to the first problem? The first problem disappeared. So the first problem was examples of oscillations. Of oscillations. Okay. Fantastic. Right. So in the last topic, we were talking about springs, and we saw that we talked about the spring constant. If you pull a spring, if you apply a force to a spring, there was the Hooke's law. So Hooke's law basically said that if you have a spring of spring constant K, you have a mass, well, just a mass, and you pull it with a force F. The force in the spring is minus Kx, where x is the displacement. So, sorry, that's not the force. The force is the force that is generated by the spring, so it's the negative of that. So force F equals minus Kx. Why minus? Well, because if x is positive, as you can see here, if x is positive, so that's 0 and that's x, then the force is negative, is to the left. If the displacement is to the right, the force is to the left, and vice versa. If we were to shift the mass to the left, the force would be to the right. So minus because the force is opposite to displacement. Does that make sense? Does this statement make sense? Does this diagram make sense? Please let me know on a scale of 0 to 10, so we can move on. Okay, excellent. So x is the displacement, is how much we move, and F is the force, that is the spring is pulling left or right depending on where we push the mass. Now, this chapter, this assignment, talks about what actually happens if you pull a spring and then you let it go. And I will demonstrate. This is a very nice demonstration. So, oh, how do I do that? Okay, so I take a mass. Okay, so a mass on a spring. And if I pull it either way and let go, it will start oscillating. This will start bouncing back and forth. Okay. What do you think will happen if I use a smaller mass? Will it bounce faster or will it bounce the same? Will bounce faster indeed. Let's check. I'm going to pull this. I'm going to pull this. So you can clearly see that the second mass, I can do it in slow motion. It clearly does more oscillations. And if we use a timer, we can time how long it takes for the big mass, for example. For the big mass, start. It takes about 1.2 seconds to complete a whole cycle. And for the small mass, it takes 0.8 seconds. Okay, so clearly the small mass bounces faster. What do you think will happen if I take two equal masses, but on different springs? So I have a short spring and a long spring. With more coils will bounce faster. Okay, so let's see. Which one bounces faster? Less coils. Why? Why do you think less coils bounces faster? If you think about it, it has to be so. But why? Why mathematically? Why? There's distance to cover. That's a good idea. It's not quite the thing. So when you cut the coil in half, well, it's actually more tension with a well, with a shorter spring, you have a bigger spring constant. A shorter spring has a bigger spring constant. So shorter spring, shorter spring. Shorter spring. Uh, Shorter spring, higher spring constant K. And that means for the same displacement, a bigger force is generated, but also means higher K, higher frequency. We won't talk about frequency in a bit, so don't worry. So shorter spring means higher spring constant means higher frequency. So these are examples of oscillations. So you have bouncing back and forth. Another very good example of oscillation is a pendulum. So pendulum, you have a bob and you let it go. You release it from a certain height and it bounces left and right. You could do it in slow motion like this. Okay. Now, let's pause this and make a snapshot. It would be interesting to know why it bounces in the first place. So what happens here, there are two forces acting on the bob. There's the weight, mg, and there's the tension. This tension in the rope or rod, whatever that is. And if you were to add these two vectors, you can add vectors by using the parallelogram rule, for example. This is the resultant force. Resultant force. Resultant force. Now, on the contrary, when the bob is on the other side, here, for example, you have mg down, you have tension along the rope, and if you complete the parallelogram, your resultant force is that way. Force. Now let's look at the spring. So for a mass on a spring, so that's a pendulum. If you're talking mass on a spring, for a mass on a spring, we always have a neutral position. So we usually call it 0. 0 is the neutral position. If the mass is displaced to the right, there is a resultant force to the left. Resultant force to the left. But if the mass is displaced to the left, the spring will push it back to the middle. So one thing that they definitely have in common, they have a force that tries to return them to the neutral position. So for the pendulum, the neutral position is obviously at the bottom. Neutral position. So in order to oscillate, you have to have a neutral position and you have to have a force that will return you to that neutral position if you were to shift from that neutral position. Does that make sense? Another example, which I can't pronounce, a ball in a ball. Ball in a ball. So you have a ball and you have a ball. A marble in a ball. And if you draw the forces, so this is the neutral position. Neutral position. And if you were to move it to the left, and you draw the forces, so that is mg, and this is the normal reaction force, you can see that there is a resultant force trying to return the ball into the original position. The resultant force. So any oscillating system, so any oscillating system has one, a neutral position, a force returning the object into the neutral position. Does that make sense? Please let me know. Please give me some feedback. Okay. So trampoline. So if you talk about a trampoline, so trampoline is also an example of oscillations. Trampoline. So if you are on the trampoline and you are pushing, so there's a neutral position is when you're standing on the trampoline, neutral position. Neutral. Now, if you move down, the elastic of the trampoline pushes you back. So there is a resultant force. If you shift down, there is a resultant force pushing you back to the top, resultant. And if you're in the air, there's gravity pulling you down. So there is a returning force trying to get you back to the neutral position. So you kind of swing. You go down, you go past the neutral position, back and forth. So that's what oscillations are. So that covers the first problem, examples of oscillations, and what do we have to have in order to have an oscillating system. So then let's talk about time period, frequency, and angular frequency. So you might be familiar with time period and frequency. You're probably not familiar with angular frequency. But it's not a very difficult concept. So the time period is how long it takes for one oscillation. The time period is the time for one oscillation. And that's obviously in seconds. Frequency is number of oscillations per second. Per second. And that's hertz. It's measured in hertz. And angular frequency, that's omega. Angular frequency. How to put it? Is the number of radians per second. So I'll give you the formula. The angular frequency is 2 pi times the frequency. So for example, if frequency is 3 hertz, then the angular frequency is 2 pi times 3, so it's 6 pi radians per second. That's in radians per second. So one cycle, one period, one cycle is 2 pi radians. So angular frequency tells you through how many cycles you go in 1 second, but it gives you in radians, if that makes sense. So if you talk about a sine wave, for example, so half a wave, that's pi, this is 2 pi. And so yeah, so one wave is 2 pi radians. So the angular frequency just simply tells you how many radians per second, if that makes sense. If you were to draw it on a circle, if you use the trigonometric circle and you imagine a bar moving anticlockwise at constant speed, well, it's the angle it turns. So omega is the angle it turns every second. So for example, omega is the angular velocity. No, velocity. So it's simply no, radians per second. Radians per second. So you should be familiar with angular velocity from the. No, I don't think you did circular motion yet. So, okay. Angular velocity measured in radians per second. The angle between the neutral line and the position. No, that's not the angle between the neutral line and the position. The angle between the neutral line and the position here, this is just the angular amplitude or angular displacement. That's not. Omega is. I'm trying to put it into words. Sorry, I've. Yeah, omega is linked to frequency. Omega is proportional to frequency. What you need to remember that omega is 2 pi times frequency, or omega is 2 pi divided by time period. Let's leave it at that. It's a really important concept, but somehow I just can't put it into words. Like it's hard to explain what omega is without referring to circular motion, which you haven't done yet. But anyways, taking measurements. So how do you take measurements? Well, the most important, let's do time period for a pendulum. So for the pendulum, we take a stopwatch and we are going to measure the time period. How do we measure the time period? What do you think we need to do? Measure frequency. Well, you can measure frequency. How many oscillations per second? Yes, certainly. But typically, you measure oscillations. So I'm going to start the timer and I'm going to release the pendulum and I'm going to measure the time for 10 oscillations. Why 10? Because that gives me a smaller error. Because I have reaction time, yeah, on the stopwatch. Okay, So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it's 10.9 seconds for 10 oscillations. So the pendulum bob, mass is 0.1 kilograms. So measurements. Mass 0.1 kilograms. Time 10.91 seconds. Number of oscillations is 10. So the time period is how many how long it takes for one oscillation. So it's 10.91 divided by 10, which is 1.091 seconds. That's the time period. The frequency is 1 divided by t, which is 1 divided by 1.091, which is 0.9165 hertz. That's the frequency. And angular frequency is 2 pi multiplied by frequency. So just multiply this by 2 pi. 2 pi. And that gives me 5.759 radians per second. So that's how I take measurements from an oscillating system. Now let's repeat the experiment, but let's increase the mass 5 times. I'm going to increase the mass to 0.5 kilograms. What is your prediction for the time? Less than 10.9. So a bigger mass will go faster. 10.91. Okay. So I'm increasing the mass to 0.5. So it becomes 5 times heavier. Okay. And start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10.81 seconds. Does it oscillate faster, or is this just my reaction time? Technically, no. If I do it again, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10.68. It's an error of measurement. That's my reaction time. So it's not bigger than 10.1. It's the same time. So the period does not depend on the mass for a pendulum. For a pendulum, the time period or frequency does not depend on mass. So does not depend on mass. However, it does depend on the length. If I take a longer pendulum, I don't need, I can increase the length. I can increase the length to 1 meter, and I can repeat the experiment. So 3, 2, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 12.373 seconds. So increasing the length does increase the time period. Okay. Increasing length. Length increases time period. Another thing that we can change is gravity. If we reduce if we make the gravity small, and we repeat the experiment, and go. 1, 2. That's going to be a long time. 3, 4, 5. So clearly, you see gravity has an effect. Increasing gravity. So gravity decreases t. I won't be able to prove the formula for a pendulum, but I'm going to just write it out. And if you believe me, that's good. If you don't, well, do an experiment for yourself and see whether my formula is correct. So it's 2 pi square root of L divided by G. L is the length of the pendulum, and G is the gravitational field. So, well, let's make a prediction. Actually, you know what? A 1 meter pendulum, should have a period of about 2 seconds. That's how I think it has something to do with the origin of the second in the first place. So you take a pendulum of 1 meter and let go. It has a period of 2 seconds, so it means it goes one swing in 1 second. So my prediction is, so if length is 1 meter and gravity is, of course, on Earth, 9.81 newtons per kilogram, and then the time period is going to be approximately, it's 2 pi multiplied by square root of L, which is 1 divided by 9.81, which is 2 pi divided by square root of 9.81, 2.006 seconds. Let's check. So length is 1 meter, mass doesn't matter, mass 1 kilogram, gravity on Earth, and let's go. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20.44. It's really close. 20.44. So measurement. So T is 2.04 seconds. Pretty neat. Do this experiment at home. Take a rope of length 1 meter. Tie something heavy to it. It has to be heavier than the rope, because if it's really light, then it won't work. So it has to be quite heavy. I don't know if you have Geomag, something like this, something heavy, and just let it go and measure the time, measure the time period, and it should give you 2 seconds for a 1 meter pendulum. Now let's talk about the mass on a spring. So okay, so let's take a 50-gram mass and measure the time period. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So mass taking measurements. So for 50 grams, so the mass is 50 grams, and the number of oscillations is 10, and the time is 5.7 seconds, and then the time period is t divided by n, which is 0.570 seconds. And the frequency is 1 divided by time period, which is 1 divided by 0.570. So that's 1.75 hertz. And the angular frequency is 2 pi times frequency, that is times 2 pi, 11.0 radians per second. That's the angular frequency. Now let's increase the mass to 100 grams. What's your prediction? What will happen to the time period? What do you think? It will decrease. Okay, any other ideas? Decrease. Anyone else? So 100 grams. Start the timer. Let's start it from the bottom. And 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8.9. 0.89 seconds. It's increased. It's bigger. The heavier mass will have a bigger time period and a lower frequency, of course. So bigger mass leads to larger time period. Now, spring constant. If we increase the spring constant, we get a stiffer spring, so you see a wider spring. Start the timer, and 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5.86. So you can see that the time period has decreased. Increasing the spring constant decreases the time period. So bigger spring constant, shorter time period. And I will give you the formula as well. The time period is 2 pi square root of m over k. Okay. And here you can here you can also try to guess what the masses are by measuring the time period, but yeah, that's another story. Okay. That's how astronauts, for example, when you are in space and you need to monitor your health. So, for example, you're on the International Space Station, and you want to know what your mass is, of course. But if you use a pair of bathroom scales, they are useless because they won't show anything. If you stand on them, they won't show anything. So what they do is they have a special device. They tie themselves to a spring, and the spring shakes them. And by measuring the time period of that shaking, they can deduce their mass because they know the spring constant. They can measure the time period, and thus they can calculate their body mass. And this is important. This is an important parameter that you have to control because your muscles get weaker when you're in space. Your body works completely differently. People who spend a long time in space have to have quite a long period of recovery when they come back because they're not used to gravity. Although technically there is gravity in space, you don't feel the effects of it because you're constantly falling with this as also the spaceship is. I want to skip ahead into year 13 and just introduce you to probably my favorite part of physics overall, which is called an electrical oscillator. So FET, that's LCR circuit. Okay. So we have something that is called a capacitor. A capacitor is literally two parallel plates, and you can charge them with a battery. So if you take a battery and you take a capacitor, this is a static charge. So one plate is positive, one plate is negative. And if you take a light bulb, you can discharge this static charge through a light bulb. So if I take a switch, okay, so I've charged the capacitor. So this plate becomes positively charged, the bottom plate becomes negatively charged. This is static charge, right? It's the kind of static charge you get when you rub your feet against the carpet. Now, if I close this switch, the light bulb will flash. As the capacitor loses charge, the light bulb flashes. And again, I can charge the capacitor, and I can discharge the capacitor through the light bulb. So the light bulb goes bright and then, and if I take the current on the light bulb, it goes, okay, it goes from large, it goes smaller, 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 smaller. This is how a capacitor works. Does that make sense? This is potentially the future of electrical devices. We might use capacitors instead of batteries. Because the beautiful thing about a capacitor is that it charges instantly. Just like that. Boop, and it's charged. And then you can discharge it through something. Okay, imagine you take your phone, you plug it in, boop, it's charged, and you carry on about your day. Or your car, you plug in your car, boop, it's charged, and then you go. This is quite cool. These are called supercapacitors, and they have the potential to replace batteries in the near future, but well, there's still technology in progress. Well, they're still working on it. Also, they're quite light, which is also very useful. And they don't use lithium, which is we have a lithium. We are facing a lithium shortage. So yeah, that's the thing. Now, I'm getting sidetracked here, but let's take, instead of a light bulb, we'll take an inductor. An inductor is a coil, is literally a coil of wires. But the beautiful thing about an inductor that it slows down the current when the current is trying to increase, and it increases the current when the current is trying to decrease. So it's sort of a restoring force, if you wish. Let's see what happens to a capacitor if we plug it into a battery. So the current, measure the current. Let's switch the battery on, and you can see the current increases, but it doesn't increase instantly, it increases steadily. So the inductor slows down the increase of current. Once again, it increases. Well, you know what? Increases, drops, increases, drops. Now, the cool thing about the inductor of the coil is that if you charge a capacitor and you try to discharge the capacitor through the inductor, through a coil, it will first prevent the current from getting too large. But then as the current tries to decrease because the capacitor is discharged, it will build up that current, charging the capacitor in the opposite direction. So I'm going to switch on the ammeter, and I'm going to close the switch and that is an oscillating circuit. It's literally two plates, two metal plates, placed parallel, and a coil of wire. If you charge the plates, it goes back and forth, back and forth, back and forth. This is another example of an oscillating system. Okay. Type 1 if you think it's cool. Type 0 if you don't. Okay. And what's even cooler, the capacitor has a parameter called capacitance, which is C. Capacitance depends on the area of the plates and the distance in the plate separation, plus several other factors, but that's the gist. So capacitance, so C is the capacitance. And L, its capacitance is measured in farads. Well, it doesn't matter what it's measured in. And L is the inductivity. And it's measured in Henry. I'm starting to doubt that it is just H. Because H, oh yes, Henry, of course. And the time period for an oscillating circuit is 2 pi square root of L times C, which kinda reminds you of that. Okay, there are other examples of oscillating circuits, so we'll, yeah. Sorry, there are other examples of oscillators, but yes. If you think of an antenna is an oscillating circuit. It just has very high frequency, and that means it has a short time period. That means it has a very low inductivity and low capacitance, and you get a high frequency, and your antenna in your phone, for example, is an incredibly high frequency. So the antenna in your phone has to have about 2.4 gigahertz. 1.8 gigahertz. Yes, I think it's 1.8 gigahertz. 1.8 gigahertz antenna. That means it has an incredibly small capacitance and incredibly small inductivity. Okay. Anyways, moving on. Equation of simple harmonic motion. The equation of simple harmonic motion is like this. It is simple harmonic motion. It looks like this. The acceleration is minus omega squared x. This is the equation of simple harmonic motion. A is acceleration, and x is the displacement, and omega is the angular frequency. Now, we say that this is a differential equation. Why is it called a differential equation? Well, you might have heard that acceleration is the derivative of velocity. So it's dv dt. Acceleration is derivative of the velocity. But the velocity is the derivative of displacement. So velocity is x dash. But that means that acceleration is the second derivative. So it's the second derivative of displacement. Acceleration is displacement dash dash is the second derivative. So that means that this equation can be rewritten as d squared x dt squared is equals minus omega squared x. This is called a differential equation because it includes a function x and its derivative. In this case, the second derivative. So x is a function and d squared x dt squared is the second derivative. Second derivative of x. That's why this is called a differential equation. It includes a derivative. Differential equation includes a derivative. Let's see if you have an intuitive understanding of differential equations. So, understanding differential equations. So let's say y derivative is 3. What is y? Y dash is 3. That's a differential equation because y is because it includes a derivative. Which function has a derivative of 3? Okay, I'll rephrase that. Something derivative is 3. What's that something? Well, the antiderivative of 3. What's the antiderivative of 3? Have we not done two assignments on integration and differentiation? 3x, yes, 3x. This is the solution. So this is the equation. equation, and this is the solution. You need to solve for y. This is the solution. Let's do another one. The derivative of y is sine, no, cos x. Cos x. What is y? Sine x. Very good. That's a solution. It's not all the solutions, it's just a solution. Solution. So in a differential equation, the aim is to find the original function. Let's do a... Well, we haven't done exponents yet. So that's a differential equation. Differential equation. Oh, let's do this one. Y double dash is equal to minus y. Can somebody try to guess a solution? Well, it has at least two solutions. It has many solutions, of course, but it has one of the solutions is y equals sine x. Let's prove that this is a solution. So y dash is cos x, and y double dash, what's y double dash? Minus sine x, which is minus y. So we have shown that y equals sine x is a solution. Because if you plug in y equals sine x, it works. Okay. I'm going to go a step further, and I'm going to say that y equals cos x is also a solution. Also a solution. Because y dash is minus sine x, and y double dash is minus cos x, which is minus y as well. So, also a solution. Cos x, solution. It actually has many solutions. You can say that it is y equals a sine x plus b cos x is also a solution. Because y dash is a cos x minus b sine x, and y double dash is minus a sine x minus b cos x, which is equal to minus y. So that's another solution, where a and b are any numbers. A and b are any numbers. Constants. Okay. Nice. So we've talked about differential equations. So let's look at this differential equation. The second derivative dash dash is equal to minus omega squared x. Now, because this is a derivative of t with respect to t, we can use a special notation. X dot is the same as dx dt, is the derivative of t. So dot x dot is the same as a derivative with respect to time, to t. And this would be x double dot. X double dot is d squared x dt squared, which is literally just acceleration. So x double dot is equal to minus omega squared x. I will try to guess a solution. Guess a solution. So the second derivative is equal to a constant times the original function. Ooh, that looks familiar, doesn't it? We've just done it. The second derivative is minus the original function. The difference is there's a constant now. Well, actually, guessing a solution. My first guess, is x equals a cos omega t. Quite a good guess, I think you would agree. Let's check. I'm going to find x dash, derivative, and I'm going to use the chain rule here. So it's going to be a omega multiplied by sine omega t, and of course with a minus. Does everyone understand why this is like this? Please let me know if you don't. I would be happy to go through this. If you differentiate this function with respect to time, you're using the chain rule, the omega, so it's going to be a stays, cos becomes minus sine omega t, and then the derivative of omega t, with the derivative of omega t, that's omega, this is minus a sine omega t, so minus a omega sine omega t. Is that clear? On a scale of 0 to 10, please. Please let me know, everyone. Let me just do a quick. So if y equals 5 sine 3x, then y dash is 5 times 3 times cos 3x. Okay? I think you would agree. So if x is a sine omega t, then x dot is the same as x dash, is a multiplied by omega multiplied by cos omega t. Does that make more sense? Chain rule. So yes, here I have cos, so it's like that. Now I'm going to find the second derivative. Second derivative, I'm going to differentiate that. So minus a omega stays, and I'm doing the derivative of this, so that's going to be omega, so omega squared times cos omega t. And as you can see, because x is a cos omega t, this is minus omega squared x. So true. It is a solution. So x double dot is minus omega squared x. Okay, this is a little bit mathematical because I haven't explained anything about this equation. What does this equation mean? So coming back to a cos omega t. Okay, I'll do another second guess. Second guess that x is a sine omega t. So x dot in this case is a omega cos omega t, and x double dot is minus a omega squared sine omega t, which is the same as minus omega squared x, so also true. So that's one solution, that's another solution. There's actually infinitely many solutions, but that's not, those are the two important ones. So coming back to the equation of simple harmonic motion of SHM. So acceleration is minus omega squared x. This literally means that the acceleration is proportional to x, to the displacement. And second, a is in opposite direction to x. And that's what we started with. If you remember, today's session started with me explaining that there's a restoring force which is trying to return you back to your neutral position. That restoring force causes acceleration. So acceleration which is opposite in direction to x. Okay. Let's take so the next section I would call which solution to use. Well, let's say we have a pendulum, and have a mass, and I displace it by 5 centimeters. 5 centimeters to the right, and I let go. So if I were to draw the displacement versus time, the initial at t0, the displacement would be 5. We start with 5 centimeters, x in centimeters. Then the spring constant. Let's say the spring constant is 100 newtons per meter, and the mass is 2 kilograms. That means that the time period is 2 pi square root of, well, let's make it 200. M over K. Over K, so it's 2 pi square root of 2 divided by 200, which is 0.2 pi, which is approximately 0.628 seconds. That's the time period of this pendulum. So omega is going to be 2 pi divided by the time period. So it's 2 pi divided by 0.2 pi. That's going to be 10 radians per second. And the frequency is, of course, 1 divided by the time period, which is 1 divided by 0.2 divided by pi, 1.59 hertz. So that means after 1.59, 2, 2, 2, 2. So the pendulum would go down, up, down, so right, left, right, left, right, left, and the period would be 0.628 seconds, and half a period would be 0.314 seconds, and the equation x is going to be x is a. Now, is this a cosine graph or a sine graph? Somebody help me with this one. It's a cosine graph. So the equation is going to be xa cos omega t. So x is a, which is amplitude 5 centimeters, 5 multiplied by cos, and omega is 10 t. Let's check if this actually holds. I'm going to use Desmos. Y equals, I'm going to use y and x. Oh, actually, no, I can use x equals 5 cos 10t. Okay, I should use y. Cos 10t. Okay, I need to use a different scale. Minus 1, 2, 4, 2. Okay. Does it look like? I think it does. Okay, so let's see. This is pi over 10, so that's pi over 4. So Oh, sorry, I'm interested in this one. Pi over 5, of course. Pi over 5. So that is, yes. That pi over 5 is 0.628. Yeah, indeed. So it does work. Yes, 0.628. So that clearly these two graphs are the same. Now, if you pull and let go, you use cosine solution. If you start from the center and you hit the mass and it swings into oscillation, then you use the sine. So pull and let go, pull and let go, use x equals a cos omega t, and hit from initial position from neutral position, then you use x equals a sine omega t, because then at 0 seconds it's the displacement is 0. So I hope that makes sense. So I want to go through problem 11, not maybe the whole thing. It is a difficult assignment, so might as well just help you with it. So a 10-gram projectile flying at 500 meters a second hits a wooden block of mass 1 kilogram, attached to a wall with a spring of stiffness 200 newtons per kilogram. Okay, so 200 newtons per meter, and sticks therein. The block initially at rest is in the equilibrium position. Find the subsequent horizontal motion of the block. So the block will go in an oscillation. So we can find the period of that oscillation. So the time period is 2 pi square root of m over k. That's 2 pi square root. Mass, well, it's 1 kilogram and 10 grams because the bullet is 10 grams and the block is 1 kilogram. So it's 1.01 divided by the spring constant, which is 200. So that is approximately 2 pi square root of 1.01 divided by 200, 0.447 seconds. So omega, the angular frequency, is 2 pi divided by time period, which is 2 pi divided by answer, which is 14.1 radians per second. Okay. Now we need to decide, is this going to be a sine or a cosine function? What do you think? Well, we need to find the initial velocity. It is a sine, yes, because it goes from the original position. So you hit it and it goes boom, 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 boom. So you need to find the initial velocity and you use the conservation of momentum. Yes, conservation of momentum. So m times u, that's the initial velocity, is equal to the mass of the projectile times the velocity of the projectile, which is 500. We can ignore the mass. Okay, well, the total mass. So that's going to be 1.01 times U equals 0.01 times 500. So U is 0.01 times 500 divided by 1.01, which gives us 4.95 meters per second. That's the initial velocity. Okay. Initial velocity, so we can work out the maximum displacement. So that we can find the kinetic energy of the block. Kinetic energy of the block is 1/2 mu squared, which is 0.5 times mass, which is 1.01. So 0.5 times 1.01 times 4.95 squared times answer squared, which is 12.376 joules. And then we know that the elastic potential energy, the kinetic energy goes into the elastic potential energy of the spring. So the spring compresses, and the elastic potential energy is 1/2 kx squared. And that is 12.376 joules. So x is equal to 2 times the energy divided by k square root. So square root of 2 times the answer divided by 200, which is 0.352 meters. And that's the amplitude. That's the amplitude. Because you can calculate the kinetic energy and you can calculate the energy stored in the spring as it is compressed. So that gives you the amplitude. So the equation of motion, is going to be x is equal to the amplitude, which is 0.352, multiplied by sine omega t, so 14.1 t. However, it is moving left, and if we assume that right is positive, that means it's a minus. And that's it. Okay, I have to go, unfortunately. I didn't cover everything I wanted today, but hopefully I've managed to give you a feeling for the topic, and hopefully you can now go ahead and solve some of the problems. I'll see you in next week, I think. See you next week, and yeah, welcome. Bye.